My name is Kaylee Champion. I am a second-year PhD student at the University of Colorado Boulder, and this is the feasibility of Cislunar spacecraft wake generation. Now, the motivation of this is to enable touchless potential sensing in cislunar space. So previously, touchless potential sensing has been investigated in the geosynchronous region, and in order to do so, a servicer is equipped with an electron beam or a UV laser, and it utilizes those to emit secondary electrons or photoelectrons and X-rays. And the energy of those emissions can then be read by the servicer and used to interpret the potential of the target with respect to itself. Now, this can be used to avoid dangerous arc discharges between two spacecraft during docking and serves as the first step towards enabling the electrostatic tractor. So the electrostatic tractor, again, involves a servicer equipped with an electron beam. And that electron beam is used to impose a positive potential on the servicer and a negative potential on its target, which results in an attractive Coulomb force. And the servicer can then use that attractive force to reorbit debris in the geo region or detumble uncooperative targets. And all this can be done without ever having to actually touch the target, which makes it a lot safer than a lot of other servicing methods. Now, the cislunar environment presents a lot of complexities that have not previously been encountered in GEO. So first, the moon travels through 4 different regions. So there's the solar wind, the magnetosheath, which is essentially a transition region between the solar wind and the magnetotail. And then inside the magnetotail, there's the plasma sheet, which is essentially a region of very high energy plasma in the center of the magnetotail. And then in addition, when the moon is in the solar wind or the magnetosheath region, a lunar wake develops. So the moon removes plasma through various processes, and then plasma is able to re-enter through various other processes. And this creates a low density complex plasma region on the eclipse side of the moon. And then in addition, the properties of that plasma vary with altitude. As the altitude increases above the moon, the plasma starts to return to those normal, undisturbed ambient conditions. Now, the focus of this study are spacecraft wakes. So spacecraft wakes occur when plasma is mesothermal, which means that the velocity of the electrons is greater than the velocity of the spacecraft, which is then greater than the velocity of the ions. So essentially, as a spacecraft is flying through, it pushes particles out of the way, and the electrons are able to catch back up and continue impacting the spacecraft from all sides, but the ions are not able to catch back up, which leaves low density net negative region on the anti-velocity side of the spacecraft. And the impact of this on touchless potential sensing is unknown because spacecraft wakes do not occur in GEO. Now, before we can implement spacecraft wakes in an experimental vacuum chamber, we need to know what the general shape and size of these cislunar wakes are in the different regions. So this is investigated using 2 tools, NASCAP2K and SPICE. So NASCAP2K is essentially America's spacecraft plasma interaction code. The computation of the space is defined by a Cartesian grid, and the geometric wake is defined by determining how much of the plasma is blocked by the spacecraft at each grid point. And the results are then presented as a fraction of the ambient density. And then SPICE is essentially Europe's spacecraft plasma interaction code. So the computational space is defined by a mesh, and it works more as a particle and cell solver. And then the results are presented as the ion charge density. So here we can see the Dayside wakes. So as seen on the left, the most intense wake forms in the Dayside solar wind region. As you can see, as that wake extends several spacecraft radii, and actually has an extended, almost vacuum low density region behind that spacecraft. And then there's another spacecraft wake in the magnetosheath region, but it's not quite as long or as intense as the solar wind wake. And then there actually is not a wake formation in the magnetotail or the plasma sheet region. And then in addition, the change of these spacecraft wake properties and the lunar wake is also investigated. So as you can see, at low altitudes or closer to the lunar surface, the bulk speed of the plasma is lower and the ion temperature is higher, so the ions are able to catch back up to that spacecraft more quickly, and we don't really get a wake formation. But then as the altitude increases, the plasma starts to return to its local ambient properties, and as a result, the spacecraft wake also starts to return. So the goal is to generate solar wind Dayside cislunar wakes, as these were the most intense wakes, and the moon actually spends about 2/3 of its orbit in the flowing solar wind. So in order to do so, the ECLIPS chamber is used at the University of Colorado, And this chamber is equipped with an ion gun at the top, as shown in the picture, that produces argon ions at an initial radius of 1 millimeter. So in order to do these wake experiments, an object needs to be able to fit inside that ion beam in order to generate a wake on the bottom of the object. However, 1 millimeter is not large enough to do this. So lenses have been proposed to expand and then refocus the wake. So previously, 2 lenses were looked into to try to generate LEO wakes. And so one of these is a thin lens design. So 2 circular lenses with openings in the middle to allow the beam to pass through are set to potentials that expand and refocus the wake. And then the other design is thick lenses, which are closer to hollowed out cylinders that again have a little bit of separation between the lenses and are set to different potentials to expand and refocus the wake. Now, before we can design cislunar wakes in the ECLIPS chamber, we need to know the constraints and set up a design method to create these lenses. So first, in order to determine the required ion beam energy, the scaling law is used to relate the velocities of 2 different ion species. So in order to generate argon ions that are representative of 400 kilometers per second hydrogen ions, which represent the solar wind, the argon ions need to be accelerated to 63.6 kilometers per second, where the beam has an energy of 835 electron volts, which is within the capabilities of the beam. The next 3 lens designs were investigated. So these are 2 thin lenses, 3 thin lenses, and 3 thick lenses. And then each lens has 3 parameters. So that's the location or the thickness, the potential, and then the inner radius. So that's 6 to 9 parameters per design, depending on how many lenses there are, which is very tedious to go through and work with manually. So optimization algorithms were utilized to investigate these lens designs. So in order to do so, a model of the vacuum chamber and the lenses were created in Simion, which is a particle tracing software package. And then MATLAB used the genetic algorithms described in a Windows batch file to modify those lenses and then minimize the defined cost function. All right, so the minimum radius is defined by the RPA. So the RPA will measure the ion properties and has a diameter of 1.2 centimeters. In order to properly measure the plasma, the RPA must be able to fit behind the object in the wake and then measure the ion properties on either side of the wake, which means that the final minimum radius must be greater than 18 millimeters. And then as shown on the left, for both lens designs, the final optimized lens is 37 millimeters in radius. So this is sufficient for conducting wake experiments. However, the first lens is about 1 millimeter away from the grounded ion gun and is set to a very large potential. So there's a high risk of arcing between the ion gun and the first lens. So in order to avoid this, the first lens is moved so that it's at least 1 centimeter away from the ion gun. This is done by first widening the inner radius and then shifting the lens so that it's 1 centimeter away from the ion gun. Both designs result in a final radius of about 23 or 24 millimeters, which is about 1.5 centimeters shorter than the previously optimized design. But fortunately, this is still wide enough to be able to conduct experiments, and it really emphasizes that the beam should be expanded as soon as possible in order to optimize this wake lens design. And then last, the thick lens design was also investigated. However, the optimization often resulted in this design where the beam is first expanded and then repelled such that the ions fly past each other and result in a fine, large, unfocused radius. However, as shown, all the ions are passing through a point at about the same time. So there's a high risk of collision, which can then cause unexpected results. And so it's not ideal for implementation in the vacuum chamber. So the lens potentials were constrained to avoid this, but the final unfocused radius is only about 31 millimeters. It is not as large as the focused radius achieved with the thin lenses. So as a result, the thick lens design is not used. So in conclusion, representative solar wind Dayside cislunar wakes may feasibly be generated in the ECLIPS chamber. And for future work, this will actually be implemented, and experiments will be used to determine if touchless potential sensing is feasible in the presence of these fast-flowing ions and spacecraft wakes.